section in our handbook. And Dean Sinnott, a former colleague of mine, who's now at another company. What we've done is we've taken a structure that is the largest buried impact crater and have turned it into an economical producing gas field. And I'll go through the story of how we did it, and it's quite a neat success story. Now, the first thing I want to show behind here is that we don't want to miss the big picture of what we're trying to do here. For an oil company, it's we're trying to make some dollars. That's the bottom line. But it is quite exciting that we're getting to combine some sort of astrogeology with terrestrial geology. I'll begin with an introduction of where and what Steen River is. Now, there's a lot of, public interest on what are impacts, the effects of impacts, and any movies like Armageddon, Deep Impact. You can go just to any bookstore and pick up books like Impact, Lucifer's Hammer Nemesis. They all talk about the end of the world. I'm not going to quite go that far, but we can certainly show you some of the damage and some of the effects of large impact craters in Western Canada. Now, you don't have to look very far to see craters. You just have to look at your nearest planetary neighbor, which is the moon, and you'll see that on any clear night that is just loaded with craters. You don't even need a telescope to see that, just a pair of binoculars. We can look at the planet. These are satellite images taken by Mariner 10 when it was flying by Mercury. This is Mercury here. You can see that the surface is absolutely saturated. There's craters upon craters. So from this, planetary astronomers are very easy or very, come to the conclusion that we must have had a very accretionary early history. We had particles perhaps the sizes of small rocks to boulders to small asteroids colliding together, and through a process called accretion, forming large planetoid type bodies. And this is the early sort of proto-solar system, the early formation of the Earth and the moon, with lots of things crashing down on the planet. Well, we don't see much of that early history. It's preserved on places like the moon, Mars, Mercury, where there's very little erosion or a very thin atmosphere or no atmosphere at all. On Earth, we do have an atmosphere. We have things like glaciers, rain and wind erosion. But we do see some evidence of impacts. Rotterdam in Africa. We see Wolf Creek in Australia. These are just small kilometer or slightly larger sized craters. Some of the smaller ones in desert areas. But we don't have to even look in Canada. Canada actually has a couple of dozen very well sort of studied craters. This one being one of the better known ones, Manitowoc in Quebec. It is roughly 100 kilometers across. The rim is actually way out over here. This is the central uplift. That's what's left of it after the glaciers and erosion. And this is like the crater bowl in here. So again, a large 100 kilometer sized object. Now, for oil and gas production, I had to convince the company how to spend $50 million and why I wanted to do this. And it was because I thought there was oil and gas here. And it was a bit of a tough sell. But especially when you have dry holes drilled off Halifax here. This is off Nova Scotia, the Montagny structure, a beautiful central uplifting structure, some 45 kilometers across. But again, a dry hole. So your boss says, well, can you do better than that? Manitoba has a large circular outcropping feature of rocks, and it too is a remnant of an old impact crater. But we're going to look at examples. I don't want to talk about examples of non-producing craters. I first had to come up with a model, and working with people like Alan Hildebrand, Richard Reed from the Geological Survey of Canada, University of Calgary, they were great resources to our company. And the best known and best studied crater, thanks to people like Gene Shoemaker, the meteor crater, Barringer crater here, a lot of our current models are results of his great early work. Now, there's a lot of geologic indicators, and the early work done, like what Dr. Shoemaker had to try and sort of disprove, was that those big circular holes in the ground were just big cryptovolcanic explosions, like large volcano-type eruptions that leave big holes in the ground. Well, they're not. They're actually caused by extraterrestrial impacts. And these are some of the indicators here that geologists use. Things like shattered cones that you can see even around Sudbury, Ontario. And, they make super drilling targets, and I'll go through that. The three things we look for in oil exploration: we need a source for the oil and gas, we need a place to put it, a reservoir, and we need a place to seal it. Impact craters do all three of those very nicely. Viewfield, Saskatchewan here. This is a small crater, only a couple of kilometers near the subsurface of Oklahoma. In Texas, we have this is our best analogy that we have to the Steen River impact site in northern Alberta. Although it's only half the size, it produced over 270 BCF of gas. That's a lot of gas. And I'll try to put that in sort of ways of relating this at the end of the presentation. But anyways, these are great analogies. Can we do this in Western Canada? Well, let's talk about the Steen River crater. It's located in the extreme northwestern part of Alberta. The Northwest Territories are just right here at the 60th parallel, about 100 kilometers to the north of us. There was not much previous work written on it here. There were some early papers in the early 70s, late 60s. Gordon Robertson, one of our competitors, presented a poster at the Ames Hope Conference in Oklahoma. And then Hildebrand and us been sort of putting out, slowly releasing some of the gravity and aeromag data. There are at least half a dozen known impact sites in Alberta, and there should be at least twice that many, or 10 times that many. And as oil companies look for oil and gas, we're finding, surprisingly enough, more and more of these round circular structures buried in the subsurface. Steen River is about 25 kilometers in diameter. It's the largest one buried in the subsurface in Western Canada. If you were to do a cross-section through here, this is produced by Alan Hildebrand, it shows you that we have an asymmetric crater. That is, the formations shown in sort of a light brown or orange here are deeper on one side of it, on the west side, than they are on the east side, indicating a hit coming from this direction. Plus, the central uplift is not the center of the crater is slightly skewed, which gives us another sort of, I'll give you that in our summary, tells us sort of the history or how this crater formed. This is a complex crater. It's not the simple bowl-like crater. It's a complex crater that has a central uplift and a central peak, and of course the rim. What's important here is that the crater is not preserved. The actual sort of original rim has all been eroded away. This occurred some 95 million years ago, and since that time, about 200 meters of sediment have been eroded away. So what we're looking at is all that's sort of buried beneath the subsurface here. And then, of course, it's been covered by another 900 meters of rock. The crater itself, in a sort of a complex crater, has lots of places where you can sort of produce or hide oil and gas. Over the central uplift is a great place to drape oil targets. You can have rim anticline features all the way, so like a donut shape all the way around. You can pinch out of formations along the rim. And an example of a complex crater is King Crater on the moon, taken by Apollo astronauts. Well, this is the slide that Alan shows that actually kills all the kimberlite people. There are people that are mining or trying to mine this crater for diamonds. If you know anything about diamonds, they form in large kimberlite pipes that are coming deep from the deep below their surface. And these slides show PDFs, planar deformation features, which is one of the diagnostic tools that geologists use to show that high pressure temperature conditions existed here that are far beyond what exists in cryptovolcanic explosions. So, what I'm trying to say here, the only two ways you can produce these features is through impacts or thermonuclear testing. So unless the dinosaurs were testing thermonuclear devices 95 million years ago, there's no way that we can explain these PDFs other than the fact that they're caused by impacts. surface, and basically the remelting caused a strong magnetic field to be implanted in that rock close to the surface and shows up. But the thing that we're looking for is the rim, and the rim does not show up very nicely, as that's where we're finding most of our oil and gas. So we have to resort to another tool. We use gravity. And gravity is just especially like this, the gravity meters were excellent in this, that we have large blocks of rock uplifted near the surface, and that it's, well, close to the surface as well. So we can start to see now some very nice evidence of structures, potential drilling anomalies along the rim, including the central uplift. This is just a close-up in here. So gravity data has been very good to us. Now, the exploration development of this feature goes back decades. This is not a new structure. Like I cannot say we were the ones who discovered it. We're the ones who realized the potential. This crater here has been explored since the 1950s. I guess they didn't know what they were drilling back in 1954. If we look at a Landsat image here of northern Alberta, this is a large lake that we call Bristol Lake. There's a competitor gas plant here called, the Paramount Bristol plant. Our gas plant right here is located just off the rim of the crater. Most of our wells drilled today are right over here. Again, I won't get into details of that image. So the first thing an oil company has to do, we've got to buy land. It's through a sealed bid, sort of a closed bidding process. So we post the land, no one knows who posts the land, and then you've got to put money into an envelope and hope you outbid everyone else. Well, we ended up acquiring some over 100,000 acres of land. We have a 100% working interest. That is, we have no partners to share our profits with. And we have a caribou protection area, which means we have to be out of there by March 15th. We don't want to disturb the calving of caribou. And there's scattered permafrost, which means we have to be very careful on how we develop the area for ground disturbances. And this is a very wet area. A lot of muscades. We can only operate here in the winter when the ground is frozen. The tools that we use, well, we already talked about aeromag, gravity, seismic. Well, we use tools that look at the subsurface, well logs. We use pressure data from testing information, and of course the rocks themselves. And bear with me, being a geologist, I must show some rock photos, so you will get to see some neat fossils. Here's a picture of a drilling rig in Alberta. Okay. The targets that we're looking at have wonderful names up here. The Upper Keg River. These are all Middle Devonian, about 380 to 370 years old. The Sulphur Point and the Slave Point. Mostly these are named after geographical formations where these rocks outcrop on the surface, but they've been carried into the subsurface here. The depth of these targets are about 900 to 1,200 meters below the surface. And this is the drilling history here. The first wells drilled in the 1950s over here, the 1954 well. We had some later wells drilled in 1958 right up over here. And then the bulk of the drilling for oil. Initially, the first target here was oil. And it started up here in the corner, drilled by Mobil back in about late 1960. But the red dots show you what has happened today. Most of the red dots here drilled by Gulf Canada here, developing the gas pool. Some of our competitors, where we didn't buy the land in that sealed bidding process, are drilling along over here. And then another competitor has the oil rights up over here. So you can see some oil drilling, the gas drilling on the northeast rim, and then some other competitor drilling here. Gulf has been very successful in its drilling plans up to date, and I'll share some of those results with you. One of the key wells fields drilled in the 1960s by Imperial Oil is a great story in that the geologists there, they were looking for a huge reef, a carbonate reef full of oil. And about 200 meters, they hit Precambrian granite rock. And the well site geologists must have been absolutely shocked to see, because they described it as volcanic rocks. They couldn't explain it. And what it was, they actually hit the uplift of the crater. So a wonderful tale when you read the ancient drilling records, not quite that ancient, but for me it is. And it's kind of neat to actually see how they tried to put the story together back then. But it all fits now in today's model. This is some of the pictures. Normally we do not see rocks that are overturned and are about 200 feet thick and then flipped upside down. You only can explain that really in sort of impact type you can imagine a lagoon, a restricted lagoon, not a lot of water coming through and out. So it's a very restricted environment. And its depth is about 1,000 meters. And there's only 2 known wells capable of production. And again, there's only maybe 1 or 3 BCF per section, and not a lot of gas. This is a pride and joy for Gulf Canada, this Slave Point Formation right up here. It has some impressively producing wells, all in the east side of the crater here to date, although there's many other shows, where show just means a potential hit all around the crater. Some of the mapping that we've done, we've looked at the top of this formation. This is a structure map showing you that as you go down, everything sort of gets deeper as you move down to the southwest. This is due to the formation of the Rocky Mountains. And you can see that there's definitely a high structure here. If you take out that slope down to the southwest, you clearly see that we're dealing with a large, again, 25-kilometer diameter, ribbed donut-like structure with an uplift here that is not shown because the slave point that I've mapped is not present. You can also see a large fault here called the Hay River Shear Zone that goes right up into the territories. We can see, this is where the rock photos come in. We can see cycles in the rocks where we have the sea level was rising. 375 million years ago, the sea level was slowly rising. The rocks were trying to grow, the carbon rocks were trying to grow and keep up with that. We call them shallowing upward sequences. And we can map the thickness of these rocks. We see them that there's trends of thick rocks trending in a north, west, southeast trend here. The cycles look like this. If you were to look at the rocks in Calgary at the Core Research Center, you'd start with a very tight line mudstone, not a good place to look for oil and gas. You'd then move into a stromatophoid veneer. These are lots of neat fossils. These are fossils that would form like in reef-type environments in today's environment. This one has a very muddy matrix though, again, not a great reef or not a great reservoir. And then we get into a very carbonate sand-like unit here called the greenstone. This place has great porosity, a good place to look for oil and gas. And then you get into what's called the bulbous stromatophoid unit, lots of fossils. But the matrix now, the holes between the rocks are now a very sandy rock unit, great for oil and gas production. So these are preferable drilling targets right here. Again, you can see the depth of about 821 meters. All right, moving right along, what do we have here? This is a pay map. This is where the reserves are all stored in this map right here. Shows you the sweet spots. The red areas are the sweet spots. Our average porosity is only about 5.4%. Highly variable permeability, that is the connectivity of those holes. The water saturation about 30%, and we average about 12 meters of pay. The temperature of the unit down there is about 47 degrees Celsius. Okay, what does it look like in the subsurface? Well, this is what the rim looks like if you were to sort of connect the dots and make a cross-section through the reservoir. You can see that we have a nice rim feature here with the best well being the highest structurally located formation. Not only that, we have stacked pay. That is, we have gas coming from a unit below the slave point, which is the sulfur point, and of course the slave point up here. Some impressive flow rates of 11 million, 12 million a day. This is a horizontal well. We actually drilled wells horizontally through this unit, and I'll explain that in a moment. Okay, this is engineering data. So Rob, this is for you, or any other engineers out here. What we do, this is pressure and time. And what we do is to test what's in these formations. We run a pipe down with packers. These are inflatable packers that can inflate and seal off the formation. You can open up to a hollow tube up to the surface. When you open up that tube, you get whatever's in that rock will flow up the drill pipe, and the pressure goes down. When you shut it in, you get the pressure building up. What I want to show with this slide is look how quickly that pressure snaps back up. That is highly permeable or very permeable rock. And we flow gas out of here too. The pressure buildup tells you something too. As that pressure builds up, if it follows a single slope, it tells you have a single or homogeneous system. If it goes on two slopes, as this diagram shows you here, time and pressure, it shows you may have what's called the dual porosity model with the rocks. That is, we don't only just have rocks or holes between the what's called matrix porosity, we also have fracture porosity. And you got to think, this is a fractured impact feature, so it makes sense. So when we first do our test, we see the fractures releasing the gas. And then over what's called middle time, we see the matrix kicking in. And then at late time, we see both matrix and fractures producing gas. This is a test of one of our gas wells here. That's what it looks like. It's we stop that flow, and then the pressure starts building up again. It took about 20 hours. But again, the pressure or conductivity is proven through pressure differential. Now, one of the things we talk about in oil and gas is skin. And I'm not talking about, one-piece bathing suits versus thong or something like this. We're talking about damage to the formation. The drilling process actually damages the rock. That is, it impedes the flow of hydrocarbons to the borehole. And what we see here, these positive numbers, the higher it is, the worse it is. So these have high skin numbers. So what we try to do is, how we try to keep, when we drill, we use drilling muds that keeps the oil and gas or the stuff in the ground that doesn't come flying out the hole. Now we drill under balance. That is, we drill without any drilling mud or a lot of drilling mud in the hole, such that while we were drilling, we were actually flowing gas. This is a horizontal drilling operation. So we actually, the hole takes a deviation, goes 90 degrees, and we start drilling horizontally through the rock. And this year we're flowing at rates of 25 million, like we exceeded the surface handling capability of the rocks. And it was quite scary for the guys out here. They were calling out, please stop drilling, okay, stop drilling. And we did. And every time they hit a fracture, the whole rig would shake. And it would jump up another 2 million cubic feet a day. Excuse me. So it's quite an impressive sight when you're going through those fractures. I was not there, so I missed one. In any event, some very impressive flow rates, some of the highest in Western Canada. And let's just show you some other information. These are the two wells we did horizontal drilling. We only went about 200 meters in one, 283 meters. This is the path they took. We tried to stay at the very top of the slave point. The reason for that, remember those top units where the best porosity was located. So we went horizontally through those units, and again, we can go at different angles. We can control those bits, like those drilling bits, like you would believe. It's really quite impressive. Okay, with all this gas, we have to build a gas plant. And we had a lot of competition from competitors to stop us, as they wanted to control the area. But with our perseverance, we were able to get through in a couple of public hearings. We were able to get it through. So what we've done, as of March of this year, we now have a gas plant producing 31 million cubic feet of gas a day and 70 barrels of natural gas liquid, which is good stuff. This is what the gas plant looks like from a sort of an aerial view. The control room over here, the gas comes in. I'll go through the process here in a minute. This is a zero-emission plant, one of the best you can get for environmental purposes. Nothing going into the atmosphere. It goes back into the ground where you don't want it, where you don't see it. Right back into the formation, so it's basically you're not damaging the environment. The well, we have only 4 wells. We have determined that we think we can drain this feature with 4 wells, although we drilled 6. asymmetry I talked about earlier was from the east at an elevation of 53 degrees. Isn't that impressive that you can learn about this? The structures can be imaged on seismic aeromagnetic gravity, has significant reserves producing oil and gas, and that people ask me, like, how much energy was that released? Well, Alan Hildebrand figured that out. He made some assumptions here that the impactor was just under a kilometer in size, had a mass of about 1 billion tons. It released 42,000 megatons of energy. That's TNT. That is greater than the entire nuclear arsenal put in one spot and detonated at the same time. A very impressive impact. And I'd just like to acknowledge my company, Gulf Canada. I'd just like to say that that one gas plant will heat 81,000 homes for a year with 1 year's production. So it does a pretty good job. The revenue to the province of Alberta, every month, we write a royalty check to Alberta for $440,000. That's 25% of, that's the standard royalty fee. So you can see what our company is making every month on that thing. Also, the Geological Survey of Canada, University of Calgary, Genetics Technology, Stokes Consulting for the forward, Spectra Exploration for acquiring that aeromag data, and of course the people I've worked with. This is a very big project, working with a lot of people from different fields in the company and in the industry and in sort of the university world, the academic world, and it's been a super project to work on, both from a career and basically part of the hobby too. And when can you end a geology talk sort of with astronomy, and that how bright and beautiful a comet is as it flies past our planet, provided it does fly past. Thank you very much.
Thanks, Ron. Questions?
Red dwarf.
Yes, red dwarf. Presumably there is a seal rock on this like point there. What sort of rock?
Okay, it is a shale. There's a Beaverville Lake shale that sits right over top. Shale is a great sealing rock. Yes.
What is it about an impact crater that makes you think it's likely to be gas from another house?
Okay, it's not so much, it can act as a source, but in this case it has provided the greatest reservoir. It has provided a raised rim with a 25 diameter circumference that has taken a rock that some of it was quite tight, has fractured it. It can produce, if you think of it now, getting back to the source stuff, it can produce a bowl that can fill up with organic shales, which can then become a source rock later in the future. But primarily it is provided Steen River, one of the greatest reservoirs in that whole area. There are no rocks around there or wells that produce at those kind of rates anyway. Yes.
How far is your plant from Eagle London?
Quite a ways, actually.
Question over the back.
Yes.
Given your economic success of the project, what are the chances of getting more substantial research funds behind investigating more impact, especially the very impact structures in Western Canada?
Well, Gulf Canada has been very generous to the impact group at the University of Calgary. We're funding additional research through more collection of gravity data. We have a lot of that data that the aeromagnetic gravity we funded, and so for Alan Hildebrand and his colleagues, it's been a great way to study more of these craters. And naturally, there's an economic interest to us as well to learn more about these features. So we're very interested in funding this type of research.
Well, do you have any guess that if you had great success in going forward with research, how many structures you find, and then, of course, the other side of it, how many of them will be productive hydrocarbons?
Okay, it all depends where they're found. If they're found on the Precambrian Shield, you might find a nickel mine like Sudbury, I guess, but those are not